In this video, we're going to look at how we can use transformer network encoders to numerically encode small molecules. What we want to achieve is the following. We want to use SMILE strings, which, as we have learned, represent the structure of small molecules, as the input for transformer network encoders. And then we want to pre-train the model for a task, which can be the self-supervised task of predicting masked input tokens. After model training, we want to extract a single numerical vector with a lot of meaningful information about the small molecule. We can achieve this by, for example, taking the element-wise mean of all updated token representations after our pre-training. Alternatively, we could also first fine-tune the pre-trained model for a specific task of interest in a similar way as discussed for protein language models. Afterwards, we can use the resulting vectors as the input for machine learning prediction models to predict a property for small molecules. The tokenization of SMILE strings is not as straightforward as for protein amino acid sequences, where it was pretty clear that each amino acid should be a separate token. Here we have different options for tokenizing SMILE string. The first option would be to simply tokenize each character in the SMILE string. Another option is to use a method to search for the most common patterns using a method of choice and making the most common patterns individual tokens. For example, we could do a simple frequency analysis based on a large number of SMILE strings, where the most common characters and combinations of characters are counted. Another more sophisticated option is using byte pair encoding, which iteratively merges the most frequent pairs of characters or patterns. This method is widely used in models like GPT and BERT. So let's have a look at how this works. First, we provide a large representative dataset of input sequences, in our case SMILE strings. And then we write down all the single characters that occur in those SMILE strings, and we use this set as the initial set of tokens, which we now want to expand by additional tokens. So now we search for the most common combinations of tokens. And let us, for example, assume the combination of an opening square bracket and a capital C is the most common combination in our SMILES dataset. This would mean we would add this token as an additional token to the set of our initial tokens. And next, we would again search for the most common combination of tokens, which we can, and now we can also include the token that we have just added. So, for example, the most common combination of tokens that currently exist could be the combination of the token that we have just added and the add sign. This would mean that we add the string consisting of an opening square bracket, capital C, and the add sign to the set of tokens. And we will repeat this over and over again. And we stop this process if a specific condition applies. For example, if we have reached a predefined vocabulary size, or if the frequency of the token that we would add next is below a certain threshold. And of course, we also add a set of required special tokens, for example, a beginning of sentence token, an end of sentence token, a padding token, and a masking token. The final option for tokenizing SMILE strings that we are looking at is using common sense and the SMILES specification rules that we have seen in a previous video. We will have a short look at how this can look like. Of course, we always have some special tokens, and then we have some single characters which we need to encode, for example, branches using parentheses, forward and backward slashes using for specific cis and trans isomers, and then we have a dash, equal sign, and hashtag to represent bond types, and we have numbers to indicate the start and end of rings. Then we also have single characters for representing different atoms that we can have. We have learned that those atoms that you can see here are all the atoms that we can write without square brackets in most cases. And we also have lowercase letters for atoms that are part of an aromatic ring. And finally, we need more complex tokens, which basically means everything that we can have within square brackets. So for example, if a carbon atom is a chiral center, we write the carbon atom in square brackets and represent it by a different token. Alternatively, we could also make the square bracket separate tokens, but since the square bracket doesn't have any meaning on its own, such as the parentheses that indicate a branching, it probably makes sense to not make those brackets separate tokens. The options for the positional embeddings are very similar or identical to what we have seen for protein encoders. One option is to learn positional embeddings during the training process. We've seen this, for example, for the ESMOB transformer network. To do this, we first need to specify the maximum number of tokens that we can provide in the input sequence. In this example here, the maximum number of input tokens is set to 512, which means we can have 512 different positions. We store the positional embeddings for all 512 positions in a single matrix with learnable entries, where each row stores the embedding for a different position. For example, the first row stores the embedding for the first position. If we now want to access the embedding for the second position, we generate a vector with all zeros and a single 1 at the second position. If we multiply our embedding matrix with this vector, this results in a single vector that has in its column the entries of the second row of the representation matrix. So this is our positional embedding for this token. When generating this matrix initially, the values of the matrix are typically set to small random values. And since all entries of the matrix can be adjusted or learned during training, we have learnable positional embeddings. Another option that we also already have learned about are sinusoidal positional embeddings, which are defined positional embeddings using the sinus and cosinus functions, and those embeddings are not adjusted during training. And another potential option is using rotary positional embeddings, or short ROPE. The broad idea of this is that instead of using some kind of positional embeddings that we add to the token embeddings, we rotate the token embeddings by a certain degree. And how much we rotate the token embedding depends on the position. For example, the first position would result in only a tiny rotation, whereas the larger position would result in a larger rotation. So in this visualization for d equals 2, we can see that the rotation amount increases with the position m of the token, allowing the model to capture positional relationships dynamically. We're now going to look at how we can train small molecule transformer networks. As for the protein amino acid sequences that we've discussed before, we can train the model for masked language modeling. This means we randomly mask approximately 15% of the tokens in an input sequence, and the model is trained to predict the type of the masked amino acids. In the context of natural language and also of protein amino acid sequences, training for this task makes a lot of sense. Because for every token position in a sentence or in a protein, there is only a very limited number of tokens that make sense to be in those places, being restricted by grammar and meaning in the context of language, and being restricted by biophysical rules and patterns that evolved through evolution in the context of proteins. In the context of small molecules that are represented through small molecule SMILE strings, however, it is often much less restricted what kind of atom we have at certain positions. Let us, for example, look at this simple SMILE string. CCO represents the small molecule ethanol, and if we now mask the last carbon atom, we don't really have a way of telling what type of atom we should have at this position. We could, for example, have nitrogen, oxygen, or sulfur at the masked position, but from looking at the remaining SMILE string that is not masked, we cannot really tell which one it is. This makes it harder to learn through the task of masked language modeling good token representations, which contain a lot of chemical information about the small molecule. What we can do instead is calculating molecular properties of these small molecules using, for example, the Python RDKit package. We have seen in the last video that RDKit has the module descriptors that computes over 200 properties for each small molecule from the molecule SMILE string. If we train the transformer network to predict those 200 properties for each molecule, instead of training it for the mass token prediction task, we force the model to extract actually meaningful information about the molecule. We could not follow the same procedure for proteins because it is much more computationally expensive to calculate such molecule properties for proteins. On this slide, you see a comparison for the Chambertin small molecule transformer network that was trained on the one hand for the masked language modeling training task, MLM, and another version of the model that was trained for the multi-task regression prediction task, MTR. And in the first column, next to the type of the pre-training task, you can see the dataset sizes that were used. Then the different versions of the Chambertin-2 models have been tested for 8 different prediction tasks. You can see 4 regression tasks on the left, where lower values indicate better model performance, and you can see 4 classification tasks on the right, where higher values indicate better model performance. You can see that in all cases, pre-training the model to predict 200 molecule features calculated with RDKit leads to better results compared to pre-training the model for predicting mass tokens. On this slide, we compare 2 popular small molecule transformer networks. On the left, we see the Chambertin-2 model, and on the right, we see the Mole-Former. Both models are based on the encoder of the transformer network. In terms of model sizes, they differ. The Chambertin-2 model has only 3 encoder layers and a hidden dimension of 600, whereas the Mole-Former has 12 encoder layers and a hidden dimension of 768, resulting in many more learnable parameters. And we have just seen that the Chambertin-2 model was tested both with masked language modeling and multitask regression as the pre-training task, but we have seen that the model pre-trained for the regression task performed much better. The Mole-Former, on the other hand, was only trained for the mass token prediction task as a pre-training task. The training dataset for the Mole-Former was also much bigger, with over 1 billion different smile strings. And both models used canonical smiles, which is, as we have seen, a method to generate a unique smile string for a given molecule. The Chambertin-2 model uses learned positional embeddings, whereas the Mole-Former uses the rope embeddings that we've just seen a few slides ago. And finally, I was not able to find any details regarding the tokenization of the Chambertin model, but from their vocabulary file, it looks to me as if they've used a method that is based on the frequency of characters that occur together, similar to the byte pair encoding that we've discussed. And the Mole-Former, on the other hand, uses a tokenization based on the SMILES specification rules, so something similar to what we have also discussed a few minutes ago. And there is no direct comparison between the 2 models, but from the reported results on benchmark datasets, it seems that the Mole-Former typically performs better than the Chambertin-2 model. This might be a little bit surprising, since we have seen that the Chambertin model for the Chambertin model, that the multitask regression pre-training leads to much better results than the mask token prediction pre-training. However, the improved performance might be attributed to the larger model architecture and the larger training datasets.